Can you see my screen?
Yeah.
Okay, good. Is it also vibrating on your side? I've got some disturbance on my screen. I don't know what's going on. Just see quickly. Okay. I think it's just this. Okay. You must please tell me when I have to start.
Yes, sir.
So, good evening, everybody. Welcome back to the third lecture of today's class. And now Professor Scholtz is going to present. I welcome you, sir, once again on the behalf of Department of Physics, Assam University, Silchar. Now, before he starts his lecture, so let me introduce him. Professor Frederik G. Scholtz is a prominent South African physicist and currently holds the position of Vice Dean Research and Postgraduate Students, Faculty of Science, Stellenbosch University. Earlier, he was also the director in the National Institute of Theoretical Physics. He got his PhD in theoretical physics from Stellenbosch University in the year 1986 and thereafter had a postdoctoral position in Germany as a von Humboldt Fellow. He joined the faculty of Stellenbosch University in the year 1993 and became the head of the physics department in the year 2006 there only. He got several awards in recognition of his work in theoretical physics, which includes the Silver Medal of the South African Institute of Physics and the President Award of the National Research Foundation. His current interest focuses on non-commutative quantum mechanics and quantum field theory. He has a number of publications in highly reputed journals. Besides, he is also referee for the journals such as Physical Review Letters, Physical Review A, B, D, etc. And today he is going to present on dynamical symmetries and its application in many body systems. So, sir, please.
Thank you very much for that kind introduction. So, as you will see,
With this, I request.
Sorry, can you hear me? Okay.
Yes, sir.
Can you hear?
Yes, sir.
Okay. All right. So I changed my title slightly because what I'm going to do is really very introductory to give you an idea of how one can use group theory to actually construct soluble many-body systems. But I will just touch the surface of this. I will give you something like 4 different examples, some of them, well, at least one of them very elementary, and then also a couple of more advanced examples, but they will all still be rather of a simple nature. There are many more advanced applications that I will not really touch upon. The difficulty I have in presenting this is that I'm not quite sure what background the audience has in group theory. So I'm going to bore you in the first lecture with introducing Lie algebras, And some of the aspects of Lie algebras that I will need, very explicitly need, in developing the later part of the semi or the small little course. Okay, so my starting point then will be the basics of Lie algebras. So I'll first talk a little bit about the structure of Lie algebras, and also mention something about the representations of Lie algebras, specifically using so-called highest weights. You may see some of this work also in some of the other lectures, I think, particularly on the structure of Lie algebras. There, I think they will use Duncan diagrams. I will use root vectors here more specifically, but they're, of course, very closely related. Then in the second lecture, I will focus on dynamical symmetries. What is a dynamical symmetry? And how they emerge quite naturally in many body systems, both Fermi and bosonic systems I will discuss. So this will be a general introduction to the idea of dynamical symmetries. And then in the last lecture, I will give specific examples of dynamical symmetries. So we'll look at the axial symmetric rotor, which is the most trivial example, basically diatomic molecules, some application to nuclear physics, low energy nuclear physics, and then also some, I will conclude with some generalizations and extensions of these ideas. But I will just mention that very briefly without going into much detail. All right, so let me start with the basic aspects of Lie algebras. So let me just say, I do not see, since I'm in presentation mode, of course, I do not see the audience. So I can't see if somebody has a question or whatever. So I suggest that if you have a question, just pitch in and ask. Or else the chair may be able to see and interrupt me. But unfortunately, I cannot see if somebody has a question. All right, so let me start. I'm going to start with defining the algebras very directly, but let me remind you that there's a whole history behind the algebras. It's not something that Lie sucked out of his thumb at some point. So it comes from the notion of Lie groups. And as you will know, a Lie group is basically a group that is at the same time a manifold. And because of the group property, these manifolds are homogeneous, so they look exactly the same locally everywhere. And therefore, it's sufficient basically to study their local properties. This is where the Lie algebra comes in. So the Lie algebra really has to do with the space of tangent vectors at a certain point. Normally we choose the origin, but it doesn't matter because it's homogeneous. And we just look then at the space of tangent vectors, and they close naturally then on what is called a Lie algebra. Okay, so a Lie algebra is firstly, it's a linear vector space. So what I'll do is this will generally be a complex linear vector space. And then you have a product defined on it, which we call a Lie product. The rule is that firstly, if I multiply two vectors, I get, of course, another vector in the algebra, so in the space. So that's closure. It's an antisymmetric product. So if I switch the order, I get a minus sign. And finally, it satisfies the so-called Jacobi identity, which means that if I take the product of 3 and I do a cyclic permutation, then it sums up to 0. So I may just mention here that a Jacobi identity has a very specific origin in terms of the group structure. It actually encodes the associative property of the group. And this is a very important property of Lie algebras. Okay. A simple example. would be just if you take all the real n by n matrices, and then in the inner the product is defined as the commutation of the matrices. You can check very quickly that the commutator satisfies all the properties that I mentioned here for the Lie product. All right. Another important concept that I'll need later on is that of a subspace or a subalgebra. So this is just a proper subspace of the algebra, of the space that I have. And in addition, it must also close under this multiplication rule. So if I take two elements in the subspace, I multiply them together, then I must get another element in the subspace. Okay. So if we have a proper subspace of this property, we say it's a subalgebra of the Lie algebra. And as you will see later on, the idea of dynamical symmetries is completely built on this idea of finding subalgebras of a given algebra. Okay. Now, of course, if I have a vector space, a linear vector space, then we can choose a basis for the space. And I'll denote the basis elements here by AI. And I runs from 1 to some value, let's say R. So R is what we call the dimension of the algebra. So it's the dimensionality of this linear vector space. And we say then that a Lie algebra is R-dimensional. If the dimensionality of the vector space is R. All right. Now, if the product, if the product closes, if we have the closure property, then obviously if I multiply two basis elements, let's say AI and AJ, then I must get another element of the algebra, so of the linear space. So I should be able then to expand it in terms of the basis elements again. So I can write it as a CIJK, AK, or I will often just use the repeated index convention here. So I won't write a sum explicitly, but just write a repeated index KK to denote that we have the sum over this. What is important to note here is that these things that we have, these constants that appear here, they are called the structure constants of the algebra. And it's important to know that they must, of course, be antisymmetric in the lower two indices. That simply comes from the antisymmetric property of the Lie product that we had here. So that's quick to check, and you can do that if you want to convince yourself. You can check that as an exercise. Another important thing to realize is that, of course, these structure constants determine the structure of the algebra. That's why they are called structure constants. But note that they are also basis dependent. So if you were to choose a different basis for the Lie algebra, then of course the structure constants will change. In fact, you can see just from the way I wrote it here that from a tensorial point of view, this would be a contravariant tensor in the lower indices and covariant in the upper index that you have here. So they will transform like a normal tensor under a basis transformation on the Lie algebra. So from that point of view, one has to be careful when you think about classifying Lie algebra. So although the structure constant gives you that information, you cannot just look at the structure constants of two algebras and say they are different or the same. You have to compare them in a certain sense, in a certain standard or canonical basis to make a decision about that. And I'll come back to that later on. And this is where the idea of the roots of a Lie algebra will eventually come in. Okay. To give you a particular example, of course, that you all know certainly by now, of a Lie algebra, then this is the one of angular momentum, which is also called the SO3 or SU2. They are isomorphic to two algebras. The angular momentum algebra, where I have three angular momenta. the JIs, where I runs from 1 to 3, or XYZ if you want to, and they satisfy this very well-known commutation relation down here, where epsilon ijk is the completely antisymmetric tensor. Okay, so I think all this stuff should probably be known to you. So let's move on a little bit. What I'll do now is to start talking a little bit about the structure of Lie algebras and how you can classify them, or the classification of Lie algebras. Okay, so if I go and I take these structure constants, C, I, J, K, and I view them as a set of matrices, I view them actually as a set of R by R matrices. And the way I'll do it is I call Ti, you see the I index here, the I index there are the same. I call this the matrix Ti, and the matrix elements, the Kj matrix elements, are just the two indices Kj. So I can organize the structure constants into a set of R by R dimensional matrices. Okay, and then if I apply the Jacobi identity, so let me remind you, that was the important identity that I have here. If I apply the Jacobi identity, then one can quickly check, and again, I think for the students, I leave this as an exercise, but it's straightforward to check that these matrices, because of the Jacobi identities, these matrices must commute. Now here, these brackets are the commutator of matrices. They must go and commute on an algebra which is completely isomorphic, the same as the algebra that we started with. So we see the commutator of Ti of Tj is Cijk Tk. There's of course again a summation implied here. So what we have achieved in doing here is to take the structure constants, organize them in R by R dimensional matrices, and then we discovered that these matrices close in an algebra which is identical to the one we started with. And this is, of course, what we call a representation. I will give later on a more formal definition of what I will call a representation of a Lie algebra. And this particular representation that we have here is called the adjoint representation. This is a very specific representation, and as you can see, the dimensionality of the matrices are the same as the dimensionality of the algebra. Okay, so let's now move on to the idea of the roots of a Lie algebra. We have now in front of us a set of R by R matrices. So we can ask the following question. Can we, well, certainly we can, but we can try to identify from this set of matrices a maximal commuting set of matrices. I will not go into more detail in this, but so we can just try to find the largest number of matrices that commute with each other. So let's suppose we can find L such matrices, then we say the Lie algebra has a rank of L. So the rank is basically the maximum number of commuting matrices you can find in the adjoint representation. And this is subalgebra. This is actually a subalgebra of the full algebra. This is called the Cartan subalgebra. And we normally denote this by a HI, where I would then run from 1 to L. Okay, now if I have a set of commuting matrices, then I can do the most obvious thing. I can say, well, since they are commuting, we can of course find simultaneous eigenstates for these matrices. So we can find states which are labeled with alpha, such that when I act with a HI on it, it gives us an alpha I. Of course, the alpha will depend, the eigenvalue will depend on which matrix I look at, alpha. So I can then, I can then take these numbers alpha I, so there are L of them, of course, and I can organize them into L-dimensional vectors, which I'll denote by alpha. So it's alpha 1, alpha 2, up to alpha L. And we call these vectors, these L-dimensional vectors, the roots of the algebra. So just as a side remark, let me say that this is a bit of a more lengthy development or proof that one has to go through, but you can show that the roots can always be chosen to be real as well. So the roots are always real valued. Okay, so now we have, of course, the HIs. Remember, the HIs are R by R matrices, so they are L R by R matrices. And so these matrices, these R by R dimensional matrices, will then, of course, have R roots, R simultaneous roots. So when I solve this eigenvalue problem, I will find R alphas or R such L-dimensional vectors that we call the roots. Now, if one goes through the full analysis, which I obviously don't have the time to do, one can analyze the structure of these roots. And what you will find is that there are L0 roots. They are exactly the same number of zero roots as the rank of the algebra. And that's actually pretty obvious because if I look at the HIs, they commute. And because they are commuting, they give rise to these so-called, well, it's not that obvious, but they give rise to these so-called zero roots. And then one has on top of that R minus L non-zero roots. Now, these other non-zero roots, this is a very important property, they are non-degenerate. So you only get one alpha. There's not a multiplicity in them, there's only one. But they come in pairs, alpha and minus alpha. So if alpha is a root, then minus alpha is also a root. So they come in pairs, but they are not degenerate. Okay, so these roots are really the tools that we use to classify the algebras with. In particular, one can use these roots to bring the algebra into a canonical form, which we call the Cartan Weyl form. So this is a particular choice of basis, if you want to, that we denote by HI and E alpha. So the HIs form the Cartan subalgebra, and the E alphas, they basically act like ladder operators. They ladder between the eigenvalues of the HI or between the roots, if you want to. And they are labeled then by the non-zero roots that we have. And in this basis, the algebra takes a standard form, a canonical form, which is that if I multiply a HI over HJ, it gives us 0. That simply comes from the fact that, remember, the HIs were chosen so that they would be commuting. So this is just capturing the commutative property of the Cartan subalgebra. Okay, then if I take the product of a HI with an E alpha, it gives me an alpha I E alpha. You see, this looks like very much like a kind of eigenvalue equation. In fact, you can rewrite this into or this is actually equivalent to this equation here, this eigenvalue equation here. And because of this particular commutation relation or this particular product rule for the HI and the E alphas, the E alphas act as ladder operators of the HI. So if you give me a certain state, let's say alpha, and I act with an E alpha prime on it, then it will give me something where the alpha has been shifted. You actually add alpha prime to the alpha. Okay, if you take the product of an E alpha with an E beta, then that gives you something which is proportional to E alpha plus beta. Okay, again, this just characterizes this fact up here, that the E alpha is basically ladder between the roots or the eigenvalues of the H's. These constants in alpha beta appearing here, I cannot cover it here, but you can actually derive explicit formulas for these numbers through recurrence relations. So it's possible to find these numbers very explicitly. Okay, and okay, these apply only now in this case if alpha is not equal to minus beta. In the case where alpha is equal to minus beta, then if you multiply the E alpha with E minus alpha, then you get something which is actually proportional to the HI. So this lies again in the Cartan subalgebra. So it has the form alpha I HI. Note here again that I have the i's repeated here, so this is actually a summation over the HI's that you will get here. Okay. So this is what we call the Cartan Weyl form of the Lie algebra. Now, what is important, and this is the key element to the classification of the Lie algebras, like you can see here, I now have, in a certain sense, I have now a canonical form, or a canonical basis for the Lie algebra. So now I can compare two Lie algebras in this basis and decide whether they are the same or not. Remember, I said that the structure constants will depend on your choice of basis, but here you compare things in a certain sense in a canonical basis. And what you really, what it turns out that the only quantities necessary to specify the basis or specify the roots are really the lengths and the angles between them. Once you have the length and the angles between the roots, then the structure of the Lie algebra is actually completely determined. And even if you go to a different basis, you cannot change the angles and the lengths, actually the relative lengths, I should say, of the roots. And it turns out that there are four possibilities that can occur for any two roots. So if you give me two roots, alpha and beta of a Lie algebra, two non-zero roots, I should say, then the only possibilities for the angles, relative angle and lengths, are that the angle between the two roots would be 90 degrees. In that case, you cannot say anything about the relative length. So either the ratio between the lengths is 0 or, of course, undetermined. When it's the angle between them is 60 degrees, then they have the same length. They must be of equal length. When the angle is 45 degrees, the ratio between the lengths can be either 2 or 1/2. And when it's 30 degrees, you find that the ratio between the lengths can be either 3 or 1/3. So normally what one does, and this is the starting point for the so-called Duncan diagrams, one does not look at all the possible non-zero roots of the Lie algebra. You look at a very specific subset, which are called the simple roots. And you can then very economically represent the simple roots through so-called Duncan diagrams. And I think one of the other lecturers will expand on that. But what is more also is once you just give me two roots, and normally one starts in with two simple roots, once you give me two roots, I can actually generate from those two roots all the other roots through what is called Weyl reflection. So basically what you do is you take the root, the two roots, you draw a line orthogonal to the one root and you reflect the other one in that line, or surface actually more precisely if you're in higher dimensions. And then you just keep on repeating that process. And in this way you can then generate the full set of roots of the Lie algebra. And once you have all the roots, then you can basically write down the commutation relations of the Lie algebra fully. The only thing you have to do is then compute these numbers, but as you said, there are also explicit formulas available for that purpose. All right, so that's, by the way, another alternative approach one can take to the classification is through the so-called Weyl groups, and that also, so basically each Lie algebra in a sense is related to an irrep of the, or irreducible representation of the Weyl group. Okay, so let me give some examples of so-called rank 1 and 2 Lie algebras. So if L is equal to 1, then of course the roots are one-dimensional. So each root just consists out of a single number. And there can only be one pair of roots as well, of course. And we can always normalize it to 1. So we would have 1 and minus 1 are the two non-zero roots. And then we also have, of course, by construction, since L is equal to 1, we also have one zero root. And this is a very well-known Lie algebra. This is the Lie algebra of issue 2, which is also isomorphic to SO3. So maybe just a side remark here. In terms of the Lie groups, when you go back to the Lie groups, issue 2 and SO3 are not isomorphic Lie groups. The fact that the Lie algebras are isomorphic just reflects that locally the two Lie groups are the same, but globally they are in fact different. And in fact, one can show that SO3 as a manifold is a doubly connected manifold, and issue 2 is a simply connected manifold. And issue 2 is in fact a cover of SO3. It covers the SO3 manifold twice. As groups, they are different, but as Lie algebras, they are in fact isomorphic. Okay, so if one looks at the rank 2 Lie algebras, there are 4 possibilities. So now keep now in mind, if I talk about rank 2, it means that the root vectors are two-dimensional vectors, so that I can represent quite easily in a plane. And if I now apply the rules, I see that there are only 4 possible values for the angles between the roots, and of course then the ratios of lengths are as fixed as I had in my previous slide. So if you take phi equal to 30 degrees, one then gets what is called the exceptional algebra, G2. If I remember correctly, it's a 10-dimensional algebra. For phi equal to 45 degrees, one gets the algebra B2. Cartan denoted these, introduced this notation of G2 and B2. But B2 corresponds to the classical matrix group, SO5. So this is really the Lie algebra associated with all orthogonal transformations on a 5-dimensional real space. Well, it could be a complex space as well. So SO5 specifically is one of the real forms of the complex algebra. For 60 degrees, one gets the algebra A2, which corresponds to the classical matrix group of SU3. And when you have 90 degrees, then one gets the algebra D2 that corresponds to the classical matrix group SO4. So SO4, by the way, can be written again as the direct sum of 2 issue 2 subalgebras. That one easily sees when you look at the root diagram for SO4. All right, so now we have a tool in place, namely the roots, which allows us to completely classify all the, at least the so-called semi-simple Lie algebras fully. Okay. Right, so more generally, if I now look not just at rank 1 and 2, but algebras of general rank, then one finds 4, well, there are some additional cases, but I'll focus on 4 classes again. which Cartan denoted by A, L, B, L, C, L, and DL. And these different algebras correspond to the classical matrix groups SU, L plus 1. So this is AL. The BL corresponds to the classical matrix group SO2, L plus 1. CL to the symplectic group 2L. And DL to the orthogonal group SO2L. So you can see the orthogonal transformations on even and on odd and even spaces fall into two different classes of algebras. On top of this, there are 5 other exceptional Lie algebras, but I will not talk about them further in this set of lectures. They do play an important role in the same context as the others when it comes to, there are some applications, let me rather phrase it this way, some applications of them also in terms of dynamical symmetries in many body systems, but that's rather limited. So I'll focus on these classes here. In particular, the interesting ones will be, well, actually, we will use all of them, as you will see, because we will be able to look at the Hamiltonian in 2 different ways, and then all these different possibilities, all 4 these possibilities will actually crop up as potential dynamical symmetries. Okay. So let me perhaps at this point here, if there are any questions, before I change gears and talk now a little bit about the representations of Lie algebras, where I have to introduce a couple of notions that will be necessary also later on. Okay, if there are no specific questions, so let me move on now with the idea of representations of a Lie algebra. And actually, representations are more important in physics than the Lie algebras as such. The notion of a representation of a Lie algebra is really simply the idea that you have an abstract Lie algebra, like I wrote before, with using this rather abstract product rule here. But what you try to do now is to find an explicit representation of this algebra, or find algebra of or set of matrices that will close under commutation, well, matrices or operators if you want to, that will close under commutation on an algebra which is isomorphic to the one that you are given. So the idea is I have a Hilbert space, and then we say this Hilbert space carries a representation of this Lie algebra A that you give me. If I can find a linear map from the Lie algebra to the space of linear operators on the Hilbert space, such that it's also a homomorphism. So what this means is if I calculate the image of A times B, this is the abstract Lie product, then this becomes now the commutator of the images. So phi of AB becomes the commutator phi A, phi B. So keep in mind this, so phi A and phi B are now, of course, operators, linear operators on the Hilbert space. So the commutator is well defined in the usual way as phi A, phi B minus phi B, phi A. Like I pointed out before, and as you can go and check for yourself, the commutator has all the properties that we require from a Lie product. So it is antisymmetric. Of course, if we have an algebra, it will close, and it satisfies also the Jacobi identity. Sorry. Okay, so this is the commutator. So the Lie product maps then onto a commutator. The dimensionality of the Hilbert space, we call the dimensionality of the representation. Okay. Then there's a another very important property of representations. So if your Hilbert space contains no proper subspace that is invariant under the action of the operators phi a for all the possible elements of the algebra, then we say the representation is irreducible. So what I mean with an invariant subspace is if you take a vector in the subspace and you apply a phi a to it, then you again get a vector in the subspace. So if you can't find a proper subspace with that property, that if you take any vector inside it, apply any phi a to it, you end up again inside that subspace, then we say the representation is irreducible. And there's a very convenient way of testing the notion of irreducibility of a representation, which is known as Schur's lemma. And what it says is basically that if the representation is irreducible, then the only element, the only operator that will commute with all the phi a's will be proportional to the identity operator. Okay, so that's a very useful test and a very central theorem in representation theory, Schur's lemma. Now we can go on and imagine that we have found a representation of a Lie algebra, and particularly we look at a Lie algebra in the Cartan Weyl basis. And suppose we find now a representation of this Lie algebra. So what that would mean is if I look at the HIs, remember the Lie algebra in the Cartan Weyl basis is spanned by the HIs and the E alphas, where alphas were the roots. So then if I apply the map to a HI, I will of course get some operator HI now on my Hilbert space. And if I apply the map to E alpha, I get some operator E alpha. So I denote these of hats to distinguish them from the abstract elements of the algebra. So when you see a hat here, you must think about an operator acting on some Hilbert space, or if you want to, you must think about a matrix. Because in most cases, these are matrix representations that we are talking about. Now, but remember that phi is a homomorphism. So if it's a homomorphism, if you look here, you will have that phi of hi times hj must become the commutator of the hj. But these things commute, so their product will be 0. And then because of linearity, it means that the commutator must then as well vanish. So we have then that the HI, HJs must commute with each other. Just like we had before, if you remember, we introduced the Cartan subalgebra as a maximal set of commuting matrices. And the same thing happens here. So the HIs must always commute with each other. And of course, if it's a rank L algebra, it means that we have, this happens for all the ij from 1 to L. Now, since these things commute, we can of course now do the same as we did before, and we can look for simultaneous eigenstates of these operators. I'll denote them by a small lambda. So if I apply hi to the ket lambda, I get lambda I lambda. So lambda I is now the eigenvalue of a certain operator hi, and there are L such operators. So you can see again that I have L such numbers, lambda 1 to lambda L. And I can again organize these L numbers, these lambda 1 to lambda L, in L-dimensional vectors, and these L-dimensional vectors are called the weights of the representation. Okay, now in contrast to what we found for roots, the weights need not be non-degenerate. So in general, you will find that they are multiplicity, so that the same weight can occur more than once. So you will have a certain weight, but there may be more than one different eigenstates related to that particular weight. So like a normal degeneracy that we would have in an eigenvalue problem. So we have a degeneracy, and in general, we will require some multiplicity index, which I'll usually denote by an alpha to distinguish different degenerate weights from each other. And then, of course, it's important to realize the number of weights that we will get will depend, of course, on the dimensionality of the representation. So in other words, the dimensionality of the Hilbert space that we are looking at. All right. One thing you will immediately note if you look at this construction is that what we are doing here is identically the same as what we did when we introduced roots. The only difference is when we looked at roots, we worked specifically with R-dimensional matrices. So you can immediately see that the roots are simply the weights of the so-called adjoint representation. So the adjoint representation is the one where the dimensionality of the Hilbert space is exactly the same as the dimensionality of the algebra. In that particular case, the roots are also exactly the weight. So the root diagram is also exactly the weight diagram of the adjoint representation. Now, let me just see time-wise. There's no break, right? Okay, so let me go on. I think I'll finish in a few slides today's talk, because I will then continue with the idea of the dynamical symmetries, which we can do tomorrow. But so let me introduce the notion of a highest weight. So you can quite naturally divide the non-zero roots of a Lie algebra into two sets, what we call a positive and a negative. Remember that I told you that if alpha is a root, minus alpha is also a root. So that naturally leads to this idea of positive and negative roots. And the way we define a positive root is that the first non-zero entry of the vector, remember the root is an L-dimensional vector, that the first non-zero entry is positive, then we say it's a positive root, and if it's negative, then it's of course a negative root. Now, it's not too difficult, well, it's a bit of analysis that one has to go through in a representation theory, but one can show that there is a unique and also non-degenerate weight that is annihilated by all the E alpha if alpha is positive. So what I mean with that is, I should perhaps go back here. If I apply the E alpha to such a ket vector, this highest weight vector, then the answer is simply 0 for all positive roots. And we call that particular unique root, that particular unique weight, the highest weight of the representation. And since that is unique, that actually gives us a way of labeling the irreducible representations of a Lie algebra. So the highest weight is a very useful tool for labeling the irreducible representations of a Lie algebra. I should actually classify that a bit more. I won't go into the detail here, but this actually only applies to a compact, semi-simple compact Lie algebras, but let's not be too technical on this. For our purposes, this is quite sufficient, what I'm doing here. So the way we can therefore label states in a general representation, well, this should be actually, I see I wrote there reducible, well, it could be, of course, reducible as well. But the way we labeled in general states of a representation will be, and this could be reducible or irreducible, will then be as follows. So we can label the states by the highest weight. That tells us which representation, which irreducible representation we are busy with. So if the representation that you give me is reducible, there will be more than one highest weight appearing in that representation. Then on top of that, I will have to specify a multiplicity factor. This tells me how many times a certain weight may occur, or distinguishes between weights that are degenerate. And then, of course, I have the weight itself. So this gives me a way of labeling the states within a general representation of the Lie algebra. And I'll use this particular labeling scheme later on to show you how one can now actually then solve for the full spectrum and the eigenstates of certain many-body Hamiltonians. Now there's another very important concept associated with Lie algebras, and this will actually play a very central role in what I'll be doing later on, and this is the notion of a so-called Casimir invariant. So suppose you have a Lie algebra, and you have found some representation of the Lie algebra. So this is now a set of operators TA. For each element of the algebra, there's a corresponding operator, linear operator acting on a Hilbert space. Then we say a Casimir invariant, C, is an operator that commutes with all the TA. So I'll say that the commutator of TA with C is equal to 0 for all A. So we call such a quantity a Casimir invariant. So as you can see, it's an invariant of the algebra. It just commutes with everything. It doesn't change. Also on the level of the group, if you apply a group transformation to it, it doesn't change. It's completely invariant. Of course, if I work with an irreducible representation, then the Casimir operator or the Casimir invariant will just be proportional to the identity. It will be some number. And the number will, of course, depend on the precise representation, irreducible representation you are busy with. In general, a Lie algebra of rank L admits L Casimir invariants. And they are monomials of the elements of the Lie algebra. So for example, if I work to pth order, I can write CP. So P denotes which order the Casimir is. And I can write it then as some numbers, which I'll denote F, alpha 1 to alpha P. X alpha 1 up to X alpha P. So it's a product of P elements of the algebra. So these numbers, if that appear here, to avoid ambiguities here, one must require them to be symmetric in the alphas. You can immediately see if they are antisymmetric, then I can take the antisymmetric part, contract the antisymmetric part of two x's here and generate a commutator which collapses to 1x. So that will then actually lead to a non-unique representation. So one has that the f's here must specifically be symmetric in the indices alpha 1 to alpha p to avoid double counting. All right, so for each Lie algebra, we have then L Casimir invariants, or rank Lie algebra, we have L Casimir invariants. The most important ones that you have probably encountered up till now and that I will use here are the second order Casimir invariants. So they will be quadratic in the generators or in the elements of the Lie algebra. So now, of course, we have an alternative way also of labeling the irreducible representations of a Lie algebra. We don't have to use the highest weights. like we did before, but we can also use the eigenvalues of the L-Casimir invariance. Remember, the highest weight was an L-dimensional vector. The weights are generally L-dimensional vectors, and the highest one in particular L-dimensional vector. So it involves L numbers. So instead of using those L numbers, we can use the eigenvalues also of the L-Casimir invariance to label the highest weight. So that gives us an alternative labeling scheme for the irreducible representations of the Lie algebra, and then also, of course, of the states of the Lie algebra. The most, like I already said, the most important Casimir invariant that I will use is the quadratic one, or the second order Casimir, which is quadratic. And in the Cartan Weyl basis, one can write it in this particular form here. So it's a sum over all the hi squared, and then a sum of E alpha, E minus alpha with alpha non-zero, sum over all the non-zero roots. And it is not very difficult, and this is again an exercise that I urge you to go and do. It is a straightforward exercise to carry out, but you can check that the eigenvalues of the second order Casimir for some irreducible representation of highest weight lambda is given as follows. So here again, know that lambda, capital lambda, this labels the highest weight and therefore the irreducible representation. A is a multiplicity index and small lambda are the weights inside the representation. So the states that span up the Hilbert space. Together with A and lambda, these states span up the whole Hilbert space in which you have your representation. And it's very straightforward to show that the eigenvalues of the second order Casimir can be expressed in terms of their highest weight as lambda dot lambda plus the sum over all the positive roots. This gives you then the eigenvalue, and I will use this explicitly later on of the second order Casimir. So this is a very convenient formula. To show it, you simply use so perhaps I can just use a hint if you want to, or give a hint if you want to check that. So what you simply do is you reorder this term in the Casimir, so that put the E minus alpha first and the E alpha second. To do that, you have to use the commutator. You know the commutator will give you back a HI. And you then use that the E alphas, if alpha is positive, kills the highest weight state. So of course you have to then break this term into two terms where alpha is positive and where alpha is negative. You will obviously see if alpha is negative, this will kill the highest weight state in any case, and it's only when it is positive that you have to do a reordering. And if you do that and use those properties, you will very quickly end up at this result for the second order Casimir invariant. So as you can see here, we can write down very explicitly the eigenvalues of the second order Casimir operators. This is not true for the higher order Casimir operators. There it becomes more difficult. There are generalizations of this result for higher order Casimirs, but at least for the second order, we have very explicit formulas for the eigenvalues. And as you will see, this is actually quite sufficient for our purposes, because the many body systems that we will be looking at will be ones where the Hamiltonian involve one and two body interactions. And whenever you have the situation of one and two body interactions only, then the second order Casimir will actually be will be completely sufficient for us to write down the eigen values of such a Hamiltonian explicitly. All right, I think what I'm going to do now is I think I'm going to stop at this point for today. It's already 1 hour. I have communicated that to the organizer, but I've prepared 3 one-hour talks because of my own time constraints as well. So what I'll do tomorrow is to just introduce the notion of chains of subalgebras. That is a key notion in defining so-called dynamical symmetries. And then I'll go on and define for you exactly what is a dynamical symmetry, how it emerges quite naturally in a second quantized system, either bosons or fermions, and how we can actually use that notion then to write down Hamiltonians, full many-body Hamiltonians that are fully solvable. We can write down the eigenstates, we can write down the eigenvalues, and we can compute a lot of other things like transition amplitudes, etc., if you want to do that as well. So I think I'm going to stop at this point for today. So let me see if I can get out of, okay, maybe if I go out of the sharing mode, I cannot page back and forth again. But let me hear if there are any questions.
So any question? Anybody has any?
I hope you could all hear me. It was very quiet on my side.
No, it's just quite audible.
Okay.
So what about Tiasha? Do you have any question, Tiasha? Tiasha, you have any question? Hello?
So I have a question.
Yeah, go ahead.
Okay. Sir, suppose I have a Hamiltonian, which is in some cases it can be written as a Lie algebra, generator, the linear combination of a Lie algebra generator. Or you can say, suppose I have a Hamiltonian, if it is a algebra element, so of some Lie algebra, can I say this Hamiltonian as a dynamical symmetry of the corresponding Lie group?
Let me answer that question tomorrow. I will give you the precise definition. You cannot generally say just because the Hamiltonian is written in terms of generated a particular group or the elements particularly algebra as a dynamical symmetry. It must satisfy a very specific condition. So it must be constructed in a very specific way to have the dynamical symmetry. And as we will see, dynamical symmetry normally also implies very specific symmetry, full exact symmetry. So there's a difference between the dynamical symmetry and the symmetry. So, but we will see that there are certain symmetries also associated with such an Hamiltonian. And only under those conditions you can say that the Hamiltonian is a dynamical symmetry, and you can actually solve it completely. You can write down at least if it's a 1 + 2 body Hamiltonian, you can solve for the eigenvalues and eigenstates completely.
Okay.
But I will answer that question in detail tomorrow.
Okay.
Any other question? Anybody has any other question? Hello, Annesha, you have any question?
Okay, now I can also see the...
No, sir, but now I don't have any question.
All right. Okay, so Bishwajit, it seems everybody is happy.
Okay, yeah.
So then tomorrow at the same time, I'll continue for again another about an hour. And tomorrow I'll introduce then the notion of dynamical symmetries. I'll talk in general first about dynamical symmetries and how they emerge specifically in 1 + 2 body systems. And then on Friday, I'll give an explicit example.
Yeah. Okay then.
Okay.
Okay. Good night and good evening to you. Good night.
Okay,
for
good
us.
night, everybody. Have a good evening. Bye.
Bye.
I think before you go, I mean, is it hello?
Hello,
Hello?
anybody?
Yeah,
Hello?
I was disconnected. I was trying to connect for a long time. I wanted to ask that is there any reference or want to share with us? Is it possible that we can look before we come for the tomorrow's class? This is essentially something new topic, at least for me.
The materials that he has spoken about today is more or less standard stuff. You can find some books like Wayborn's Lee Group and things like that.
Okay, sir. Okay, sir.
Wayborn.
Yeah. So, Professor Scholtz, he told us already that he will take 1 hour class every day, though it is 1.5, 1.5 hours by our schedule. But since he has some other problems, so he will take 1 hour every day. So that is why we are winding up, quickly. But this is, as Professor Chakraborty has told, these are almost standard stuff. So any group theory book will give, any proper book will give this these information. So I think participants can go through those if they wish, and then I think from tomorrow he will. Yeah. So internet connection is a problematic one. I don't know whether everyone is getting it. Like the lectures, I was disconnected a few minutes back. By the time I got connected, he has left.
Okay. Yeah, that's what I could see that you are not present.
Yeah, because I could not. I thought it was showing me that you are disconnected and we are trying to connect you, and it was going on. So this happened.
Okay.
So better.